In this lesson, we review the basics of modular arithmetic used in RSA algorithm, the Fermat's-Little theorem, Euler's totem theorem, where the RSA is based on. We also show how the exponent computations can be simplified based on the factorization in modular arithmetic for big number computation such as 248 bits computations. RSA is based on modular arithmetic, which is covered in number theory. Typically, the number theory is covered in discrete math course. For those who are not comfortable with modular arithmetic covered here, they should review and learn the discrete math, in particular the number theory. A mod n has a value called the remainder r after a divided by n. Here n is called modulus. And here a can be represented as a equal q times n plus r, where q is a quotient, r is less than n, and r is greater or less than 0. For example, 11 mod 7 equal to 4. Why is that? First, we compute the q, the quotients, as the ceiling function of 11 divided by 7. 11 divided by 7 is 1.514, which is the largest integer smaller than 1.514. And it is therefore is 1. With 11 equal to 1 times 7 plus r, we then can derive the remainder is 4. Same for minus 11 mod 7 equal to 3. It's kind of tricky in the sense that here we have negative number. First, we compute the quotients q to be the ceiling function of minus 11 divided by 7, which is minus 1.514, which is the largest integer number smaller than minus 1.514. It is minus 2. With minus 11 equal to minus 2 times 7 plus r, we can derive r equal to 3. A and B are said to be congruent modular n if A mod n happen to be equal to B mod n. The two remainder is the same. We express as A followed by the concurrent operator, which is 3 bar in parallel, followed by B, left parenthesis, mod n, right parenthesis. It is a very strange, weird notations, but once you get used to it, you understand what it means, and it can interpret quickly. Basically, say A and B has the same remainder after each divided by n. Know that when A and B are congruent modular n, there exists an integer k where A equal to B plus k times n. So this modular equation, current equation, is actually can be translated into actual equality equation here. A equal B plus k, some k times n. A lot of time we do this kind of translation in the proof. These two expressions have the same meaning. The left side expression using congruent operator, the right side expression using the equal operator, we know for a long time. We can verify ourselves that 73 and 4 are congruent modular 23. Similarly, 21 and minus 9 are congruent modular of 10. A and 0 are congruent modulo n if A is divisible by n. Here we show that modular arithmetic actually preserves the commutative law. Here are two of them: associative laws, distributive law, and the identity and additive inverse property. And they can be used in the proof. Pierre de Fermat, a French lawyer and mathematician in 1640, very early on, in a 1640 letter, present this Fermat-Little theorem, but he does not provide the proof, only the claim. And the claim is if P is a prime and A is a positive integer not divisible by P, then A to the power of P minus 1 is equal to 1 modular P. Leonhard Euler, a Swiss mathematician, he's also a physicist, astronomer, logician, and engineer, who made very important and influential discovery in many branches of mathematics, including pioneering contribution in analytic number theory. Here is Euler provided proof of Fermat-Little theorem. Consider this is a beautiful proof. Consider set P, which is equal to 1, 2, 3, all the way to P minus 1. So they are P minus 1 number. Multiply each element in set P by A mod P to form set X. Now we have a set X. The first element is A mod P. The second element is 2A mod P, and so on until the last element P minus 1 times A mod P. None of the elements in X is 0, since P cannot divide A. We can prove by contradiction that no two integers in X are equal. We do that by if JA is concurrent with KA mod P, then J should be equal to K. Why is that? Because we cancel out the A there. Since we know none of the element in P is equal, therefore J and K shouldn't be equal. Therefore, X consists of integer from 1 to P minus 1, because they are P minus 1 element and they are all different. Multiply the number in set P and multiply the number in set X. We now have equations. So the equation turned out to be A times 2A times 3A and so on until P minus 1 times A is equal to 1 times 2 times P all the way to time P minus 1 mod P, and in congruence kind of equations. A to the power, we abstract A out, then we have A to the power of P minus 1 times P minus 1 factorial is concurrent with P minus 1 factorial under congruent modular P. We cancel out, there's a common term P minus 1 factorial. We cancel that out, and then we have A to the power of P minus 1 equal to 1 modular n. Basically saying A to the power of P minus 1 is congruent with and 1 are congruent on P. Here we verify Fermat little theorems with a small example and illustrate an efficient method for computing modular exponent. Even when the numbers such as A or P are very big, and in particular, ISA algorithm, those numbers can be as large as 2048 bits, or sometimes in a newer one, people start to choosing key that is 4096 bits kind of number. So let A equal 7 and P equal 19. Let's prove that 7 to the power of 19 minus 1 and 1 are congruent modular 19. First, 7 to the power of 19 minus 1 is equal to 7 times 7 to the power 18. We can take the exponent 18 and factor it out based on the power of 2 series. So it's equivalent to 7 to the power of 16 times 7 to the power 2. We can calculate then 7 to the power 2, and then calculate 7 to the power 4, 7 to the power 8, and then 7 to the power 16, because each of them is a multiplier of previous term twice. And using the modular 19 number. Note that some of these operators are equal, not the 3-bar concurrent operator. Some of them are these congruent operators, therefore they have different meaning. After we compute 7 to the power of 2 to be 49, we find 49 equal to 2 times 19, which is modulus plus 11. Therefore, 11 is a remainder. So 49 and 11 are called congruent modular 19. For 7 to the power 4 is equal to 7 to the power 2 multiplied against itself. Since 7 to the power of 2 and 11 are congruent modular 19, we can substitute 7 to the power with 11. So therefore, the term 7 to the power 4 becomes 11 times 11 modular 19. And we then take the 191, the result of 11 times 11, we find out it's a number equal to 6 times 19 plus 7, and therefore 7 is a remainder, and therefore 1 to 1 and 7 are congruent modular 19. Similarly, we find out 7 to the power of 16 and 7 are congruent modular of 19. Once we have all these terms, we then can compute the 7 to the power of 16 and 7 to the power of 2 number. We can plug in to 7 to the power 18. And this gives us 7 times 11, which is equal to 77. And now let's compute the remainder by 77 equal to 4 times 19. And then we find out the remainder is 1. Therefore, 7 to the power of 19 minus 1 and 1 is indeed congruent modular 19. That proves the theorem when applied these two numbers is correct.